Hi everyone, welcome to this tutorial of Matlab Simulink. It's Amir Hossein and today I'm gonna simulate a single phase full wave semi-controlled bridge rectifier. The only difference between a full wave semi-controlled rectifier and a full wave full controlled rectifier is that we substituted the two thyristors with two diodes. To begin with, I open the Simulink, I add the power GUI block and change its type from continuous to discrete and reduce the sampling time to about 2 2 microseconds and click OK. I'll add two thyristors and I select it from the power electronics library. Okay, we don't change the variables here. And another thyristor, I add a diode. Another diode. And RLC series, RLC branch. Let's check it, that's okay. RL. We also need an AC voltage source. I'll put it in here. So let's connect our elements. I connect it from here to here, this one here, and diodes together, our branch, our power supply. Let's change the positive pole to here. It actually doesn't have differentiate. We also need pulse generators for our terraces. One for here and another one for here. Our pulse generator variables should be this, that's okay. And our frequency is 50 Hertz. So the period is 0.02 seconds. And we set our phase delay to 10%. Okay, we do the same for this one. Our period is 0.02 and our phase delay we set it to 0.12 because it should have a differentiate with the other one. We click on OK and we should set the RL branch. As you can see, our resistance variable is consistent, but our inductance variable is changing. So I set this to 5 ohms and I set this with a changeable variable called L and it is set by the millisecond. It is scaled by millisecond and I define it in here. I click on this icon, go to the callback, init functions, and I set up apply. So this parameter is defined. Set the voltage source. Our RMS voltage is 220. So we should calculate our, let's check it. We should calculate our peak voltage. It is 220 multiplied by square root of 2. So it is 311. We set it 311. And phase degree is 0 and frequency is 50 Hertz. Now we need a bunch of voltage measurements and current measurements. I think we will need 4 voltage measurements and 3 current measurements. Okay, we want to measure the value of voltage around the thyristor, voltage of our diode, and voltage of our power supply, and what's up, that's okay, voltage of our branch. Let's see, I don't know why it's still showing the error. We defined it. Let's check it. Yes, we have. Maybe it's solved later. So, and we also need current measurements. One should be here. Let's copy it. One here. Current of our power supply. And the other one should be around here. Current of our load. So we also need a scope. We have 6 inputs, so we should set to 6 inputs. Let's see, signals and ports, number of ports, 6. Okay, we set them. The register and this one in here. Okay, and that is all right. I also want to uh, limit our sampling time to for only 4 cycles. I set it to 0.08. So let's run our program. So we defined our inductance, but we didn't define the exact value of our inductance. So we should go to our script. In here we should define the value of our inductance. So the as you can see, our resistance is consistent, but our inductance is not consistent. 0, 1, 100. We should here set the name of our Simulink file, which is full wave underscore semi control. We should be careful about the capital or small words. So here we should set the value of each of our inputs and send it to our workspace. So from the setting menu, logging, log data to workspace. This is our scope data name, and we should save the format as a structure with time. Click on OK. Still, it gives us an error. Come back to here. Scope data, signals, 1, because we want to see our first signal. Here, the name of our scope. In our first plot, we want to see the voltage of the diode. As you can see here, the first signal is referred to our diode voltage. Let's diode voltage for RL changes. It's better to name it as our V voltage of diode. In the next line, we name our axis. The horizontal one is time. The next one is our the voltage of diode per voltage, and that's it. Legend. And that's the end. Let's check it. Still not working. The problem is probably from our code. So as you can see here, this is the parentheses. So let's run it again. As you can see, it is plotting the diode voltage for different variables of our loop. So in the next lines, I want to plot the thyristor's voltage. So to begin with, I only need to copy our previous code. So they won't be changed. This is our voltage of our thyristor, and here thyristor. We should catch our second signal, because as you can see here, our second signal is connected to the voltage. So we also should change it to figure 2 and thyristor voltage. So let's check it out. So as you can see, these are our plots. At the end of this video, I will discuss each plot in details. So let's copy this again. In the next line, let's see what do we have here. We are having the current of our power supply. Okay, actually it is our input current. Okay, and we should, that is okay, figure 3 and I in, and here I in amperes, in ampere. Okay, I think everything's fine except this input current. Let's check it out. While it is calculating, I write our next code for the power source voltage. And let's check it out. I think we are having problem here with our variable. What's the problem? Okay, we should change it to I. No. Let's check. It's our first. Second, it's our third line. This one is I. Okay. Let's see the voltage of our source, which we call it V input, the voltage of our input, again V input, the force signal, plot number 4, input voltage, and let's check if everything is right. Plot T V, that is okay. Next line, we want to see it's the fixed signal. Let's see what is the fifth signal. It is the current of our load. So this is the output current, I out. I out, and in here I out plus I out. Output current. Output current. So it looks fine. Let's write our last line of code. 6, and let's check output voltage. It's obvious that we want to see the voltage of our load. V out, V out. So, and this is V out voltage. So let's check it out. So now let's discuss the details of each plot individually. Let's start with the input voltage for RL changes. As we can see here, our inductance load didn't have any changes on our input voltage because our power supply is independent from any changes in our circuit. And let's check the input current. As we can see here, by increasing the inductance variable, the input current tend to be in a DC form. It's because that due to the formula of V equals L di divided by dt, our voltage and actually our current tends to be DC by increasing the amount of our inductance. The next figure is the diode voltage. As we could expect, it had no change on the voltage because the voltage of our load doesn't depend on the inductance of our inductance. So this is independent. The conclusion over our diode plot is also true for the thyristor voltage, and it has a slight change during the starting point, which it is working. As we can see here, the inductance didn't have much effect on the output voltage because the amplitude and the voltage frequency is dependent on are more dependent on two factors. First, the domain and frequency of our power supply and the time that our pulse to the gate of the thyristors are triggered. And for the final plot, we can see the output current, and we understand that by increasing the inductance, we can reduce the current ripple. And also, we understand that the current is dependent on the time that we trigger the gate of the thyroxines.
I hope you enjoyed this video. Subscribe me for more tutorials and I will upload the script codes in the description below.